Hi, I'm JJ and this is Byron. This video presents the Rubik's Cube solving robot project, nicknamed Cubers, which stands for Compact and User-Friendly Bot for Efficient Rubik's Cube Solving. The project was supervised by Michael Zenere and supported by the ECSE faculty. Rubik's Cube is one of the most popular puzzles in the world, invented by a Hungarian architecture professor named Erno Rubik in 1974. It served as an educational tool at that time for 3D spaces, but quickly became a pop culture icon in the modern world. The mystery of the Rubik's Cube stems from the challenge of solving it from one of 4.3 quintillion possible configurations. Now that we know about the Rubik's Cube, why are we doing the project? The purpose of the project is to design a robot that can apply one of the complex computer algorithms to solve the Rubik's Cube. It has significance in STEM education by bridging theory with practice and acts as an inspiration to enthusiasts of all ages. The cost effectiveness and ease of reproduction of the project also increases accessibility to a wider audience. Furthermore, the project can spark future innovations in Rubik's Cube solving robots. The current set of Rubik's Cube solving robots in the field are very limited in terms of features and availability. There are not that many for sale, and those available are expensive. They also provide no explanations on how the robot works or what algorithm is used to solve the cube. Most importantly, most robots have a fixed cube with no way to easily remove and interact with the cube. Following the introduction and current state, we have our four main project aims: autonomous, educational, accessible and reproducible, and inspirational. Autonomous refers to solving the Rubik's Cube without human intervention using the knowledge of software and hardware design. Secondly, the project must be educational by providing detailed explanations of how the robot works and having interactivity with the cube. Thirdly, the robot must be accessible and reproducible by anyone by providing public access to the software code, CAD models, and minimizing material costs for recreation. Finally, the project in general aims to be a demonstration of the robotics capabilities in hopes of inspiring the next generation of STEM enthusiasts.
The general design of the robot can be seen here with 5 motors each controlling a single face of the cube, apart from the top face. The top face is left free to allow the camera to more easily capture the cube state, as well as allow the user to access the cube by sliding the motors back and forth and attaching or detaching the cube from the robot. We can see the robot in action now.
To control the robot, a user interface was coded with Python to Kinter library. This provides direct control of the robot with features like solve, scan, scramble, toggling between fast and slow speed, and sending manual moves to the robot. There is also a timer and counter to track the solve performance. The cube state displayed on the right live updates as the robot solves the cube. Now we'll go on to the demonstration of the GUI. Here's the scramble function. This is the quarter turn. This is the half turn. This is the fast speed. And this is the slow speed.
As you can see from our robot design, we only use a single camera to capture all 6 sides of the cube. This is done by placing 4 mirrors beneath the bottom 4 corners of the cube, with each mirror accommodating for all the blind spots for the top camera. The mirror angles and camera geometry were calculated using the dimensions of the robot and the camera specifications. To detect the colors of the cube, we sample the RGB value of certain pixels in the image, with each data point representing a cube tile. These data points are classified using a machine learning algorithm called k-nearest neighbors. This algorithm works by grouping data points to the closest k-neighbors in the training dataset. To improve our color detection accuracy, we first covered the orange face tiles with black stickers to help better distinguish orange from similar colors like red and yellow. Another problem we encountered, as seen in the image on the left, is that the underside of the cube is a lot darker than the top face of the cube, which can cause incorrect readings. To correct this, we added a light source to light up the underside of the cube and also use a normalization technique called adaptive histogram equalization. This is a technique which changes the data point value relative to the average pixel value and standard deviation of a local area of an image rather than the entire image itself, like regular normalization. This makes the data points more robust against different lighting conditions and improves color differentiation. Once all the colors for each tile is calculated, the cube state is known and can be passed on to the solving algorithm. Before continuing, let me explain the Sigmaster notation used for cube solving. R represents a 90-degree clockwise turn for the right face, R2 for a 180-degree turn, and R dash for a 90-degree turn anti-clockwise.
After obtaining the cube state from the camera, a computer algorithm called the Cosiemba two-phase algorithm is used to determine the required moves to solve the cube. A scrambled cube starts in group 0, where there are 4.33 quintillion possible positions and all moves are valid. The first phase uses a search algorithm to find the moves required to transform the cube into group 1, where there are 19.5 billion positions. The second phase repeats the search from group 1, but transforms the cube to fully solved in group 2. The project will use a slightly modified version of the algorithm written by Elias Franta in C++ that only considers solutions for 5 faces.
In terms of electronics, the computer vision and solving process is done by a computer, which then sends the solving steps to a PSOC 5LP microcontroller. We use the PSOC to control the stepper motors by sending a sequence of step signals. We use NEMA 17 stepper motors, which were powered by A4988 stepper motor drivers, all of which were connected to a 12-volt power supply. Here is the final assembled circuit and the detailed circuit diagram on the right.
To interface the stepper motors with the 5 faces of the cube, a grip mechanism has been designed and 3D printed in the left image. The motor side fits the shaft of the stepper motor shown in the middle image, while the cube side is specifically designed to have a tight fit with the center of each face in the right image. The center caps of the cube must be removed for this. The holders for the mirrors were also designed and 3D printed. It has an angle of about 30 degrees to the horizontal, and the mirror can be slotted on top like the right image. These are placed around the cube as explained earlier. The motor holders shown here are used to hold each stepper motor. They are designed with 2 long slots at the bottom to allow screws to guide the sliding motion. The stepper motors are secured to the holders using 4 screws as shown on the right. All the 3D prints for the project are listed here with the corresponding time taken and filament cost using PLA material on an Ender 3 V2 3D printer. In total, it took about 21.5 hours and only 206 grams, which maintains a low cost for the project. The construction of the robot starts with 2 custom 6mm clear acrylic sheets separated by 6cm standoffs. The mirrors are soldered into the mirror holders and spaced around the bottom stepper motor holder and double-side taped to the top platform. 4 wooden blocks are placed between the mirrors to lift the 4 other stepper motor holders up. The blocks also allow the motor holders to be loosely secured using screws and let them slide in and out to freely interact with the cube. The wires are then connected with the circuit stored between the 2 acrylics. The final robot can be seen on the right. A camera holder is clipped to the side to position the camera on top of the cube. Here's a demonstration of the removal of the cube. Some tests have been conducted to evaluate the performance of the robot. On average, it takes 12.6 milliseconds for the camera to capture the image, process it, and determine the cube state. With the cube state, it takes about 15.3 milliseconds on average to find a solution using the algorithm library. Separate tests for each turn type, including quarter turns, half turns, as well as fast and slow settings, have been recorded in the table on the right. For fast turns and an equal mix of quarter and half turns, it takes an average of 163 milliseconds per turn. Using the previous average time per turn result, we're able to determine the average time for the robot to solve the cube for different move lengths at fast setting, shown on the left. We also simulated 10,000 scrambles in the benchmark and obtained the distribution of solution length on the right. 21 move solution was the most common. Using weighted average with this distribution, we were able to calculate the average time needed to solve a random scrambled cube.
In terms of the outcome of our project, the dimensions of the robot are quite small, being only 20 by 25 by 25 centimeters. The total weight of the robot is quite light, being only 3.6 kilograms. And the total cost of the robot is only $160, which is quite cheap compared to the rest of the market. The average total solve time was only 3.44 seconds. Our project is entirely open source with software and CAD models in our project repository, which can be seen through the QR code on the top right corner. In terms of how this project can be built upon, we can further improve the color detection to make it more invariant to different lighting conditions. We can also improve the portability by using a Raspberry Pi instead of a computer, as well as using a battery instead of a power cable. And ideally, we would like the user to place the cube in any orientation, because currently the cube has to be placed with the blue face pointing out for the robot to work.
Thank you for listening.